Zoom. Okay. Today I'm going to work through, going to basically work through one problem, kind of which connects a couple of the magnetism concepts together, and then maybe talk about homework, and maybe we'll see how much time we take today, and then towards the end I might make a couple comments about the extra credit that you probably picked up yesterday, but didn't really kind of spend any time talking about that. Just wanted to give an idea. It says in the extra credit that we would kind of do one aspect of the front page problem together in class. It gives the answer to that, but I said we would spend some time on that. So that might be another thing we put some time to at the end of today's class before we're having a 4-day weekend. And next to see you guys on Wednesday. The other thing to say is in the schedule, it says our next test is going to be a week from today. That's going to be the following Monday. So it'll be about circuits and magnetism, basically chapters 30, 31, and a lot of the lab work we've done on circuits and on chapter 32. We may likely, especially with moving that test back one day, probably next week, start to get into discussing chapter 33 a little bit, but that won't be on the next test, which is a week from Monday. And that would be like yesterday's lab topics, concepts, induction. Okay. All right. Let's consider this scenario, and we're going to work it through kind of once, and then we're going to kind of want to spend just a little bit of time after doing this problem thinking about good old right-hand rule. And maybe something we've talked a lot about, it's kind of built into using the cross product. Whenever you use the cross product, the idea of a choice between two opposite vectors has been kind of made for us when we do the right-hand rule, when we do our cross products, and we kind of make those choices in the same way every time, just to be consistent. And that's probably the most important thing, is kind of making those decisions the same way every time. So we're going to maybe do this problem once all the way through, and then we're going to consider maybe at the end, before leaving this problem, we'll consider, well, what if we did the whole thing with left-hand rule? Or like, what does and doesn't matter about use of right-hand rule? And we'll get some insight into that maybe as we kind of head out from the first half of our class. So I kind of wanted a straight edge. Straight edges. Okay. Did it snow where you guys were this morning? Okay. I hadn't quite gotten to campus yet. Feel like I'd feel better about everything if I just like hadn't looked outside for about 45 minutes, because then it would have been kind of gray day, a little bit damp. Look out 45 minutes later, same thing. Like, oh, okay. But it snowed. Okay, so here's the question. We're going to have two objects. I'm just going to kind of use straight edge here. There's going to be a long straight wire. And this one's going to carry a current. Oh, this pen's getting a little dull. This one's going to carry a current. Maybe we'll call this one I1, because there's going to be another object up here which also has current. So maybe I1 will be 5 amps. And then I'm going to draw another object up here carrying some current. It's going to be a rectangular loop, and there'll be dimensions to the loop. No real dimensions to this long wire. It's essentially infinitely long. And then let's see here. Let me get this about right in dimensions. Okay. That's 5. Okay, so about like this. It's going to be a rectangular loop. And I'll give you the dimensions here and how far it is away from the wire. The near edge is going to be 2 centimeters from the wire. The dimensions are going to be 3 centimeters and 6 centimeters. Let's maybe call this you know, length and width, if I use some variables to refer to that, length and width. And it's going to be carrying a current, let's say this direction. So around the whole loop, I2, and that one maybe will be 2 amps. And what's the one more piece of information you might want to know about this setup? How far away is the rectangle from the near wire? So that'll be the other guy to label here. And this distance here will be 2 centimeters, and that I think is actually drawn to scale on the sketch here. 2 centimeters. I don't know really what I want to call that one. I guess it's kind of like a radius, but it's not our only radius, so I kind of hesitate to call it R. I think I'm just going to call it A. Okay. So this is the arrangement. Get a little tighter, maybe left to right at least. This is the arrangement. We're going to talk about this one maybe for the next 15, 20 minutes. What might you be curious to ask about this arrangement? What would a good part A or part B? So how is the red thing affecting the green thing? Even if you can't see the colors, it's green. How is the green thing affecting the red thing? That's one thing. You can see things better online, colors and some of these details than on the projector. Something like that, I think would be some of the good questions to ask. What are typical questions we might ask? You know, find the magnetic field strength at some location near a certain source. Find a force or a torque on some object, maybe especially a current in a wire or a loop. So I think the main question here will be, will there be a net force? I'm trying to ask it a little generally, but that would be kind of where I'd want to go. Like, what's the force between the red and the green thing? Is there a force of red on green? If so, what direction, how strong, and vice versa? Of course, Newton's third law says if you can answer one of those questions, force of red on green, you've answered the other one, force of green on red is the same strength, opposite direction. Which way do you think it'd be easier to do the problem? If our goal is to find the force between them, do you think it'd be easier to think of it as, I'm going to try to figure out the force that the red object applies to the green object? Or do you think it'd be easier to try to do with the ingredients and tools we have and we're used to and we're comfortable with? Do you think it'd be easier to do figuring out, like kind of thinking of this as the source, green as the source, and what is the force that green is applying to red? Which one do you think would be helpful to think of as the source, and which one do you think would be helpful to think of as kind of like the test object, or the object of interest?
Maybe the wire is the source.
Why that way? That's what we're going to do.
The wire is infinitely long.
And we've got a ready to go formula for magnetic field of an infinitely long wire. So if we start out thinking of red as source, we can do that. If we did it the other way around, you would either need to look up the magnetic field formula for a finite wire, which you can. We hadn't written it down. I think it's in the textbook. I'm not sure. Or we could go back to the integral we did for the long wire and just change the limits. But we could do that. And then we have to add up 4 of those contributions to get like the overall field due to all the green wire. And then we'd have to probably do an integral for the red wire, and we could. Or we could look up a formula, which would probably only be kind of an approximation, so probably not as good for, like, well, unless you had a formula for the magnetic field of a rectangular loop. But probably I think what you'd actually find is kind of a formula for a magnetic dipole, and then you'd approximate the loop as a perfect dipole. It's not a perfect dipole if it's got a physical size to it. It's a perfect dipole if it's a really, really, really small loop. And then we talk about things like area times current times number of wrappings. Anyways, we definitely are going to kind of think of this as the source. So this is going to be our source, and this will be our object or objects of interest. Maybe each leg can kind of be an object of interest. test object. That'll work out pretty well. So let's just kind of take the first half of it. So what we get to do here is we get to do both halves of chapter 32, right? We get to do the first half, which more we talked about second, which is if you know the source, can you find the strength of the magnetic field? Can you find the magnetic field vector at a given location nearby? Find B. And then we're going to use B to find something else, like a force or a torque, force in this case. I think we should also ask a question about torque, maybe, by the way, in passing. What's the force of red on green? What's the torque of red on green? So when you let the green guy go, is he going to feel a net force and want to accelerate in some direction? And is he going to feel a net force moment and want to rotate or flip in a line in some direction or orientation other than his initial orientation? So what is the first half of that? So we're going to go from kind of like I1, I think I'll call it B1, and B1 is going to mean magnetic field due to current 1. So like, so this is like doing a source of magnetic field calculation. And then we want to go from like that to force on to, and this would be kind of like an effect, the effects of magnetic fields, effects of magnetic field calculation. So the first part is pretty easy. We have an exact formula we use quite a bit for a long straight wire. What's the magnetic field due to a long straight wire? I just want to kind of schematically sketch it out. So we do our right-hand rule. Everywhere above the magnetic field wraps around the wire in a certain way. If the current is coming at you, you're going to see counterclockwise wrappings. And that means that above the wire in this sketch, we're going to have a magnetic field pointing out of the page, a dot. And if we wanted to think about something below the wire, that would be X into the page. But in general, we're going to get a bunch of, kind of like out of the page dots. Let me try to do this a little bit. And maybe a little more widely spaced as we go up. And everywhere up here, B is going to point out, or B1 is going to point out. Everywhere down here, not that I really care, but just for thoroughness, the magnetic field due to number 1 will point away from the viewer into the page. So B1 is going to be in everywhere down there. But we don't have any objects down there to react to that field. Okay, how strong is that? B1 is mu naught times I1 over 2 pi times radius. And radius means, perpendicular distance measured from the bottom wire. Perpendicular distance from the long red wire. And I just want to mention something that I'll come back to. I just used right-hand rule once, right? To label the dots versus X's. Okay. So I think that's pretty good for the red half, actually. And now what would somebody do? Somebody want to kind of give us an idea how they would proceed at this point. The goal is to find what is the force on the green loop. Or actually, I would say maybe a good step would be, let's draw a free body diagram of the green loop, and then we can add up the forces that appear in our diagram to get a net force. So what would somebody do next? I would probably take the loop one at a time, because what do I have for a force equation? I have an equation for force on a straight wire segment of length L. And I got 4 straight wire segments. If it were circular, I'd probably have to do a differential version of that and integrate over like a non-straight section. So what's that formula that we're going to kind of need to do the second half of this? The main formula we're going to need for the second half is things like force magnetic on a straight wire is I, the L vector of the wire, cross B. And if I were to write that out, this would be something like, this is going to be magnetic field due to number 1, current affecting the current in wire 2. So like the L would be the length vector for each side of the loop. So let's think about this just directionally. Which direction is each leg of the wire going to feel a force before kind of putting the magnitudes to it and to it? Which direction would the bottom edge feel a force, right edge, top edge, left edge? Maybe I'll do that as force will be purple. So you do the L direction, which is basically the current direction. We usually write it as the L vector. That's kind of, it's fairly standard not to think of current as a vector. A wire can have an orientation, and the orientation is kind of given the vector direction. So in this case, I've got magnetic field out, and I'm trying to, I got like this kind of setup, and I'm doing green cross red. And what do you get if you do green cross red for the bottom wire? I think I get that. So downward. So this whole edge here feels a downward force, which you could either kind of draw as like a single vector maybe at the center of that wire, or you could almost kind of represent as a bunch of short little vectors all the way along, indicating that every little segment's getting pulled down, down, down. I think I'm going to do it that way. I think I'm going to do that way just kind of visually. So it's like every little segment of this, every little centimeter of this, well, centimeter is not a very long distance. It's too long of a distance for this picture. I'd say like every millimeter of this is going to feel kind of a downward force. So overall, there's going to be a net downward force on the bottom edge. What about the next edge? Or if I just kind of go around the loop, what about the next edge? Kind of like this. And then you just kind of go around the loop to there and around and around and around. You can just do it separately. But overall, this is going to, I should have done these longer. Make those longer. Because they're going to get shorter as I move away from the wire. So I wanted those to be maybe a little bit longer at the start. So this would feel a fairly long force to the right, the bottom millimeter. And then the next one, a little bit less and a little bit less and a little bit less, down to like some minimum. And pretend that those kind of smoothly changed in magnitude. You know what I'm saying? And then the top edge is going to feel a bunch of short vectors pointing away. I could do right-hand rule one more time. Current or length vector is that way. Magnetic field is out, and my thumb points up. So all these feel real short vectors upward. And you can add those up to get a net force on the top loop. And this equation will work really well on the top loop and the left bottom loop. And then the right would be short, longer, 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 longer. Pretend those matched up. Okay. Something like that. And if your goal was just to find the net force on the loop, which is the question we're trying to answer, how many times would you use this? What direction is the net force on the loop? Which sides do we need to focus on and calculate numerically, and which ones maybe don't we need to? The right and the left are going to cancel out. As long as it's not like a rigid loop, as long as it's not like some flexible stuff, it will really matter. And that's kind of nice because which segments of the wire will this be easier to apply to? If you had to just answer the force on one leg at a time, which sides would it be easy to apply this to? The magnetic field changes strength along the right leg. The magnetic field due to the bottom wire is strong at the bottom of the right leg, weak at the top of the right leg. And how would you find the force on the right leg? You'd have to kind of put this in here, put this magnetic field formula in there, and then integrate over L values, DL values from the smallest radius, 2 centimeters from the wire, to the maximum radius, which is 2 + 3 is 5 centimeters from the wire. And if you did that, you would get some net force rightward, but it would be canceled by this guy at the top and the bottom. So what do we get for the force on the top? Or yeah, how about the bottom? The bottom. I think the direction is going to be negative J hat. And how strong will the force be? It will be current I2. I should have given myself some more space, I think. Current I2, length of the bottom edge. The length of the bottom edge is what I was calling L, so I think I'm just going to call it L, not W, not A, L. And then you multiply by the magnetic field everywhere along the bottom edge, which is a constant. That's what this is kind of made for. This is the magnetic field force on a straight segment wire in a uniform magnetic field, probably best thought of that way. And then we get mu naught I1 over 2 pi. And then what should I put in the denominator there? The distance from the wire to the bottom edge is A. And vector FM top is going to be upward. And the only difference is going to be what? Same current in that leg, same length for that leg, same magnetic field, same current in the bottom wire, and this is going to be 2 pi, and then it should be like A plus W. Maybe. Sound about right. And I'm just going to say FMR or FML equals negative FM, left is opposite of FM right. So they add up to 0. We're not going to maybe express it. If you wanted to express the right and the left, it wouldn't be too bad. You'd do an integral, and your DL would be your variable of integration. You could almost think of it as a DR, and your limits would be integrating from R equals near edge 2 to far edge 2 plus 3, or A to A plus W. And otherwise, this would be very similar. I think I would write DL, and then maybe I'd write DR, and down here I'd put an R instead of A, and then I'd do limits of integration from R1 is A to R2 is A plus size of loop. Okay, so what do you get here? Let's put some numbers to this actually. What are those individual numbers? But you could also just kind of sum those up. And of course, we're going to get downward. And then I think we're going to get something like, basically we get one contribution of negative 1 over A and another contribution of positive 1 over A plus W. And you could kind of work that out as well. I think this is what you would get if you did the net force on the loop, force on the loop. I think you're going to get negative J hat. I know you're going to get length, I2 mu naught, I1 2 pi. It doesn't seem too avoidable there. Mu naught, I1, I2, L 2 pi. And then I'm just going to kind of say you would do something like 1 over A minus 1 over A plus W, because I've already kind of factored out the minus sign. And if you do that subtraction, what do you get? A plus W over the common denominator minus A over the common denominator. And when you subtract, you just get a factor of W. So you would get LW over A plus W. And maybe double check, but I believe that is correct. But let's just put the numbers to it. What's the force on the bottom? What's the force on the top? And what's the net force? Okay, first of all, magnetic field at the top, maybe I'll put that number over here. B at the bottom and B at the top. I think I'll just write those numbers for as intermediate steps. Mu naught is 4 pi e to the minus 7 times current in the bottom wire is 5 amps divided by a factor of 2 pi, which of course mu naught over 2 pi ends up being just 2 times 10 to the minus 7. 2 pi times the near edge is only 2 centimeters, which I'll write as 0.02 meters, 0.02 meters. So I think the magnetic field of the bottom edge is 5.0 times 10 to the minus 5 Tesla, which by the way is 5 Gauss, or sorry, no, 0.5 Gauss. That's 0.5 Gauss. And then if I redo that calculation by replace the radius in the denominator from 2 to 5, I think we will get pretty easy number. This time we'll get 2 times 10 to the minus 5 Tesla. Of course, both those point out of the page, or you could say positive K hat. And then if I take those magnetic fields and I multiply by I2 and the length of the top and the bottom in both cases is 0.06 meters. So I'm going to take I2, which is 2 amps, times length 0.06 times that guy. And this time I got negative 6.0 times 10 to the minus 6 newtons J hat. And this is going to be something newtons J hat. It's also going to be times 10 to the minus 6 newtons. But it won't be quite as strong because the magnetic field went down by a factor of 5 to 2. It got divided by 2.5. So this will get divided by 2.5 and gives us 2.4 times 10 to the minus 6. And if you add those up, of course, they cancel out. And I think you get negative 3.6 times 10 to the minus 6 newtons J hat, or in the negative J hat. And somebody wants to double check that when you kind of evaluate all this, you get this number. That'd be great. Let's see. Mu naught over 2 pi. So I'm just going to do that. Just double. Okay. 4 pi e to the minus 7. I'm just going to do it this way. Times 5 amps for the bottom, times 2 amps for the loop, times 0.06 times 0.03 divided by 2 pi times 002 times 2 plus 3 is 5. Did I really do all the calculations right? I got 3.6 times 10 to the minus 6. Every once in a while, things happen without a mistake. I think that's correct. If you look at this expression here, I mean, this is, we could do this in pieces, calculate along the way, or keep it in variable form to the end. If we do this here, you do see this combination come back together or come together. I2LW. Why might I kind of focus on I2LW? Because that's what we would probably call the magnetic moment of that loop. Number of wrappings times current times area enclosed. And the effect overall is proportional to the magnetic moment of this loop. The AA plus W stuff is probably it's kind of like an average value for radius from the loop. It's probably in some sense kind of doing like something about like average value or averaging or integrating and doing something for us. We're more than A away. We're always more than A away. We're always closer than A plus W away. Maybe we should divide by like some distance squared. How about something like that? Anyways, that's what you would get. And overall, are these guys, what kind of force are these guys applying to one another? They're overall attracted to one another. The bottom edge is attracted strongly. The top edge is repelled, but not as strongly. And overall, there's attraction. Parallel wires have attractive forces. Anti-parallel wires have repulsive forces. And if you want to figure out the force on the left and the right, you could do that. I think you would integrate. And what kind of integral would you get if you integrate 1 over r? Because that would more or less be the variable of integration for the right edge. It's got the same current I2. It's we're going to make dl the variable of integrate. We're going to make L dl the variable of integration. B is proportional to a bunch of constants in 1 over r. What do you get if you integrate kind of like dr over r? Like 1 over x. You get natural log. So I think there'd be some natural log expression for the right and the left edges if you want to know how strong that outward force is. It would probably be natural log, and then you'd evaluate far distance over near distance. It would be something like natural log of 5 centimeters minus natural log of 2 centimeters, which ends up being the natural log of 5 over 2. And 5 over 2 is 5 over 2, 2.5, something like that. So it's attracted. Two follow-up questions, which I said we'd get to. What about torque or desire to rotate? What if you were asked to find the force moment on the loop? If you can find it on the loop, you've pretty much found it, equal and opposite on the wire. And then maybe something about how many times did we use right-hand rule? But what about torques or rotations? When you let this wire go, he wants to accelerate. When you let the loop go, he wants to accelerate towards the wire. Maybe not very strongly. We didn't get huge forces. They were 10 to the minus 6 newtons. But if it were light, or if you cranked up the magnetic fields by, cranked up the currents, you could make that bigger. But maybe it's just really light. So it wants to accelerate downward. What about torque? What about force moments? Is he going to want to kind of like flip around or? He likes the orientation he's in. He just wants to get closer to the wire. If you pull on anything in the way those little purple, like small force vectors indicate, or in general, if you just had one big force downward here, one medium strength, small force upward, maybe a medium one right, left. If you pull on something up or down, but you pull down more, it's not going to flip it around. It's just going to accelerate it. Right and left to cancel out. What direction, now let's just think about this. What direction is the magnetic field, what direction is the magnetic dipole moment of this loop? What I've got sketched in red is the magnetic field due to the bottom wire. What about the magnetic field of this own guy himself, which is kind of like parallel to his dipole moment? Then you would do maybe like this kind of thing. You say current is circulating around the green that way, so at us. So he's already aligned with the magnetic field he's sitting inside of. But he's not sitting inside of a uniform magnetic field. If you put a loop inside of a uniform magnetic field, he'll never feel a net force. He just might want to line up. But if you put him inside of a non-uniform magnetic field where one edge is stronger influence than the other edge, then maybe there's partial cancellation, but not total cancellation, and there's a net force. This guy lines up. This guy's already lined up. It lines up quite well. Okay. So there's a couple thoughts. The net torque is 0. Let's see. Okay. Last question about this one. What if claim and answer. Claim, if you set up the current this way and you set up the current this way and you let this guy go, he's going to accelerate that way. Is that something that you think you could actually go into lab and kind of connect up to like test that prediction? To like see, is there a force on the loop? And if so, which direction? Do you think you could do that in lab?
Yeah.
Yeah. So we can kind of imagine doing an experiment to pretty much confirm or reject our expectation of a net downward force on the rectangular loop. If that's the case, should our answer about the direction really depend on this weird right hand versus left hand kind of choice?
So if you had the current going the other way, it would want to, like on just the wire, it would want to rotate.
Which wire?
Red wire. If you had it going the opposite way, the
Yes.
loop would no longer be aligned to its magnetic.
It would no longer be like, it'd kind of be like two magnets opposite in orient, like with their south poles kind of facing each other. And if you had it perfectly lined up south to south, it might not flip. But if it was at all a little bit off, it's going to feel a torque taking it away. It would, if we flipped it, there would be no torque, but it'd be an unstable equilibrium where this is the arrangement that's balanced right now. But if you move out of this alignment at all, it's not going to come back to this alignment. It's going to be like the compass needle swinging and pointing the opposite way. So that is true about, I think, kind of what would happen if we flipped one of the two currents from the way shown. So what I'm trying to think of is this. What if you did the whole problem using left-hand rule? How much would change? How much wouldn't change?
You basically just have the opposite signs on everything.
Some things are going to get the opposite sign. And if enough things get opposite signs, maybe some things by the end of it end up getting the same sign. So, I mean, we can unambiguously set up a current to flow in a certain direction. Like that's not like an arbitrary kind of mathematical choice. Like let's call the current to the left or to the right. Like that is something we can do unambiguously. And then we can have the current flowing around this in a certain orientation. So what would change if you redid the whole problem and you had been told I hat cross j hat is negative k hat? You know what I mean? And don't do it with the right hand, do it with the left hand. What would change? What would change? We use right hand rule to assign the dots and the x's in red. And I didn't kind of write it here, but I'm going to kind of add it back in over here. The magnetic magnetic field vector would have been, in all cases, it would have been positive k hat. So I'll just kind of add that, pretend that said positive k hat. So the magnetic field would switch from what we said. Somebody says, oh, I use right hand rule and I think the magnetic field points out above the wire. And somebody else says, what? You're supposed to use left hand rule, or I usually use left hand rule, and I'm pretty sure the magnetic field points in above the wire. But then what happens down here to get these vectors? You have to use right hand rule again to cross the current direction in each leg of the loop with the magnetic field direction that you think you should use. And actually all the purple stuff will stay the same. Everyone, the person who uses right hand rule start to finish and the person who uses left hand rule start to finish agrees that the bottom edge feels a downward force and the top edge feels an upward force. Not strong, and they all agree that there's no torque and that there's a net downward force of 3.6 times 10 to the minus 6 newtons. The only thing they disagree about is what? The only thing they can't quite come into total agreement on is what? The magnetic field direction. And actually that's kind of a personal human choice a little bit. Is like, what direction do you want the magnetic field to be? Kind of like, which one do you call the North Pole and which one do you call the South Pole, basically. And if you go back and you kind of take, let's go back to electrical stuff. If you go back to electrical stuff and you change all your positive charges to negatives and all your negative charges to positives, basically you go back and you look over Ben Franklin's shoulder, literally, when he was like writing down notes in the late 1700s. And when he points at one thing and calls it plus, you're like, minus, plus. Everything works out the same. That's actually testable. Like, how will things move? Will they accelerate up or down? All that will come out the same. But along the way, one group of people will be saying electric field points this way, and the other people will be saying electric field points that way. But then when you ask them, okay, but what will the force be on an object? How will it move? Will it accelerate or decelerate? Will it curve and hit the left wall, or will it curve and hit the right wall? All those conclusions, which are actually like directly testable by observing things, will be agreed upon. And
technically, like the magnetic field pointing a certain way can relies on the same objective choice, doesn't it?
Like North Pole versus South Pole, magnetic field this way or that way is something like that. And yeah, very much so.
As long as you're consistent with it.
Yeah, so there's two things. You got to be consistent with it. But what if somebody starts a problem halfway through? What if somebody starts a problem halfway through and they say, there's a loop and it's sitting in a magnetic field that points out? That's like me coming into the middle. And now like there was a choice made previously by the person that gave me that information to say the magnetic field points out. And whatever choice they made, I need to then continue to use. But if you were to say, could you rewind instead and just tell me where all the currents are? Then we could kind of have freedom and do it either way and come to the same conclusion about forces, torques, etc. So like, what would an example be in some other context where cross products show up? If somebody says something like the angular moment, I don't know, an object feels a moment in this direction. How does it move or how does it rotate in response to that? Well, they actually kind of made a choice right-hand rule to say the moment points this way instead of that way. And then you got to use it the rest of the way. Otherwise, one person says, I think it's going to spin this way. And the other person says, oh, no, it's going to spin that way. And that's something that we shouldn't disagree about. There we go. it's almost always one right-hand rule to find B, and then one right-hand rule to use B and find something more physical, like a field. Sometimes a vector like B is called a pseudo-vector, which basically means if you kind of looked at the world in a mirror, all the vectors flip, but all the pseudo-vectors stay the way they used to point a little bit. And things shouldn't depend on that. The physical results of experiments won't depend on pseudo-vector orientation. All right. Yeah. And again, if you wanted to, you could go back and you could contrast this result with one we did, I think, Monday, which was a rectangular loop in a uniform magnetic field. I think the directions were a little more interesting that day because I wanted it to have a net torque, but the net force came out to be 0 because it was in a uniform magnetic field, and this one's in a non-uniform. And you could kind of, the analogy there would be something like if you put a bar magnet in a uniform magnetic field or a compass needle, which is a bar magnet, it'll maybe want to spin and line up, but it's not going to like shoot across the page. But if you put it in a non-uniform magnetic field, maybe there's a close by North Pole over there. Then it might be attracted or repelled and actually feel a net force. Okay, that was a good one. Okay. Piece of paper here ready. Well, let's at this point maybe just talk about homework a bit. How people feel about the homework. Next week's homework is 2 questions and it's back to circuits. They're kind of challenge questions a little bit. They're a little bit more involved mathematically. I can't remember what one of them is at the moment. And it's also to just kind of remind ourselves before the test that there's going to be circuit questions on the test, basically. How do people feel about the homework? 5, what was it, 5, and a bunch jumping all over the place. Any of those on people's minds? What was your favorite one? That's usually my favorite question to ask. What was the best one? I think I've got 5, 13, 60, 39, 82, 17, 46, 48.
I thought 82 was pretty fun. The one where
82.
we're looking for pitch.
Yeah. Oh, God, what a great question. The uniform, yeah, they kind of define this thing for us and they kind of label the diagrams for something. A uniform magnetic field, we have a direction, which is positive Z. We have a strength, great. Millitesla, still decently strong. Positive charge. An electron that's negatively charged enters the region of magnetic field with a speed of blank v, 10 to the 6 meters per second, at an angle of 30 degrees above the XY plane. So I think they're kind of drawing it as if it's in the ZY plane up 30 degrees, but basically 30 degrees above the XY plane would be fine. Find the radius, lowercase r, and the pitch p of the electron spiral trajectory. That's a good one. People curious about that one. I was also wanted to just kind of point out, what was the one in the 60s? I've got the number here. 60, 46, 48. Oh, not 60. Sorry. Yeah, 46 and 48, I think are kind of interesting ones. They're not too long. How did people think through number 82? Let's just talk about that one maybe a little bit. We never kind of explicitly calculated anything with this kind of helical spiral path, but we did mention that it won't be a perfect circular path if you kind of have your initial speed or velocity be in certain directions. Maybe you'll get something helical. Anyone want to say how they found? I would probably find R first and then move on to find P later. Anyone want to say kind of how they found radius? We have a ready-to-go formula, right? There's one that I'm fairly used to, which is radius of a circular path of a charged particle, radius of a charged particle's path in the presence of a magnetic field. Did they write that one in the chapter summary? Not quite, but we did. What's that formula for radius as it relates to magnetic field? I'm thinking of this one here. These kind of two formulas here. I think we wrote things very similar to these guys. Radius of the circular path, and then you could use that in velocity to find time for one orbit and take the reciprocal of time and get period, or sorry, that is period, take the reciprocal and get frequency. What do you have to, what velocity should you plug into this one? Did people do it kind of this way, a little bit differently? I would say basically we can go here if we're smart about what to plug in for V. We know mass of the object, I think it must be given, right? Charge of the, oh, it's an electron, sorry. Electron. I would usually write that with an absolute value on Q because I want everything to be positive. What's the, and B, we got B. What do you plug in for V? I think I might have wrote it slightly differently. I wrote it, or maybe I didn't. Do you want to plug in the full velocity or just one part of the velocity? Just the velocity that points how? What's that? Yeah, like perpendicular to B, and they put B on the X, or sorry, they put B in the Z direction, K hat, so we only want the magnitude of the velocity perpendicular to the magnetic field. So you could start talking about like V perpendicular and V parallel. That's what I would kind of naturally do. And in this case, what's V perpendicular? Magnitude times cosine of 30. So the velocity that's going to lead to the circulation is magnitude times cosine 30. And then that's part of the answer. And then what could you do for the rest? Find the time to go around once. And then just multiply the parallel velocity in the Z direction by that time interval, which is basically a reciprocal of this. And the time to go around does not depend on the object, right? The time to go, sorry, depends on the object Q and M. It does not depend on the speed of the object. So you could find this frequency, take the reciprocal, that's the time to go around once. And then the time to go around once times the parallel component of V would be your answer. And you can probably do all that with cross products back from the beginning, but that's, I think, how that one would work out. Kind of an interesting thought. If you make it all parallel velocity, you get a straight line. If you make it all perpendicular velocity, you get a repeating circular path. And if you're somewhere in between, you get this. How does the fact that it's a negatively charged electron instead of a positively charged object affect things, or how does that come into play? It just changes which direction these spirals spiral. Like which, do they spiral clockwise as they corkscrew up, or do they spiral counterclockwise as they corkscrew up? And the size is just about magnitude of charge and mass, and the distance for what they're calling pitch P is probably still just about magnitude of charge and mass. Could you tell from this diagram whether the object following this curving path is positively or negatively charged? Because I'm hoping they drew it correctly to be consistent with what they said it was. It's a negatively charged electron. I would pick any one moment, any one dot along the path, and consider what's the velocity, what's the magnetic field, and what's the force. And what directions does the force point as you go around? I guess it's almost hard to tell. You could probably look at that and say it's going one way or the other way. I was kind of imagining it's going into the board, out at the right, out at the left, into the right, out at the left, into the right, out at the left, into the right. So let's say you picked a point over here. It's feeling a force that way. So I've got velocity coming kind of at me and upward, but more or less at me. And I've got a magnetic field pointing up. Actually, that would point this way, which is good because that's saying a positively charged object would feel a force away from the axis, and then the negatively charged object towards the axis. So I think they got that right in the sketch. Yeah. Well, you guys know what a positron is? It's like an electron, but it's positively charged. Same mass as an electron, opposite charge. It's the antiparticle of an electron. So if they'd said, is this an electron or is this a positron? You'd kind of look at it and say, oh, it seems to be inconsistent with right-hand rule. It seems to fit with opposite of right-hand rule for like a negative charge. So it is a negatively charged object. It's probably a positron or a negatively charged object of a given charge and mass ratio. If you took measurements on this, let's say you just fired a particle in here and you just watched it move. Let's say you knew the speed of the particle. You knew the speed, but you didn't know what the particle was. And you watched it spiral like this. What could you figure out about the particle? You can figure out it's negatively charged. If you took measurements on radius and pitch, you could figure out, what could you figure out about the particle? So like, let's say you know R, you know F cyclotron, because you make measurements on this trajectory. What's that?
You type in prime Q and M? I'm not sure. I guess Q per M.
You would never be able to find Q on its own or M on its own. Why not? Because every magnetic influence is going to be multiplied by Q to give you a force and then divided by M to give you an acceleration. Kind of like that. And same for electric forces. Any electric field thing is going to be proportional. The force will be proportional to the charge Q, and that's a force, but then what affects motion is acceleration divided by M. So you'd be able to figure out Q over M, charge to mass ratio. So you wouldn't go to like, let's say your job was to identify the particle. You could kind of look up, here's the charge of electrons, positrons, here, and a bunch of other things. Here's the charge of a pion, a kaon, nucleus of a helium atom. But what would be most relevant to how it moves is the charge to mass ratio. How do you think somebody ever actually figured out individually figured out the charge on an electron and the mass of an electron, instead of just figuring out about the charge to mass ratio?
So how it acted to forces that weren't electric or magnetic?
You'd have to have a non-electric force or a non-magnetic force in the problem. And it would be kind of similar to like, a little bit different, but kind of similar, like if you only have gravitational forces or things that in essence are due to gravitational forces, you can never learn the mass of anything by watching it move, right? Because what happens when you fire a cannonball off a cliff and you fire a pen off the cliff? If you give them the same initial speed and everything's just gravitational, no air resistance, no other stuff, they follow the exact same path because their mass to mass ratio is all one. In this case, you'd figure out the charge to mass ratio, but you wouldn't know, is it a huge object with 50 electrons, with a mass of 50 electrons, or a smaller one? All right. Why are the northern lights the northern lights? Maybe we'll say that quickly. Why are the northern lights the northern lights? Why don't we see these weird ripply things in the sky as often at our latitude or near the equator? I'm trying to, they show the picture here and they show a little diagram here and they show a diagram. They show a diagram here. Here's the spiraling, right? What if these blue lines kind of start to curve around? Well, the spirals kind of move to follow the curves. You wrap around the magnetic field. If the magnetic field gets stronger, your wraps get tighter, like smaller. If the magnetic field gets weaker, your wraps get kind of big and lazy. And so what if you're in an environment like this and you're a charged particle that kind of starts to encounter the Earth's region? You start to get near the Earth. You kind of get funneled along these curving magnetic field lines, which are like a dipole field with one pole near the North Pole and the other pole near the South Pole. And you get kind of funneled around so that they don't really come into the lower atmosphere at the medium latitudes. They tend to come into the lower atmosphere funneled near the North Pole geographically or the South Pole geographically. So then what happens? What makes the lights? where's that light come from? If they're flying across outer space, you don't get the lights. You have a bunch of charged particles just flying across the solar system, mainly from the sun, but that's life in outer space. There's like high energy stuff flying around. And if you want to go live in outer space for a while, you got to wear shielded stuff that's going to protect you from the high energy radiation, because right now we're being protected. What's protecting us from the high energy radiation? The atmosphere is kicking out a bunch of that stuff so it doesn't reach the surface at high levels. So where do the lights come from? When these charged particles moving at high speeds start to encounter the molecules of the atmosphere as it gets denser and denser, they kind of crash into the molecules of the atmosphere and they hand off a bunch of energy to like the molecules in the atmosphere, and the molecules hold on to that energy for a little bit of time and then give it away in the form of light, pretty much. And those collisions of incoming solar wind particles and interplanetary charged particles are going to happen much more often near the poles because of the shape of the Earth's magnetic field. If you were to look at this diagram, maybe one more thing, which end of this, based on your understanding of how to draw magnetic field lines correctly, which end of this is the magnetic North Pole end and which end of this is like the magnetic South Pole end? Magnetic field points away from what kind of pole, loops around and points into what kind of pole? Points away from a north magnetic pole and points into a south magnetic pole.
So the North Pole is the South Pole, and the South Pole is the North.
Yes. So when you get into this, sometimes you should just back up, slow down every once in a while and say, oh wait, do you mean magnetic North Pole, or did you mean like geographic North Pole? Because they're kind of more or less opposites, and then they don't perfectly align either. So like the Earth's south magnetic pole is in the Arctic northern hemisphere, but it's not like right at the Earth's geographic North Pole. It's up there, and it moves around. Like over the last 120, 30 years, it's moved around a fair amount because it's reflecting all the charged particles in the Earth moving around as the Earth rotates, in some sense. So it's flipped. So why is it flipped? And that's kind of annoying, right? Kind of annoying. It's true. The North Pole needle of a compass points geographically north, or nearly geographically north, but that means it's pointing towards a nearby south magnetic pole. So that's maybe something to keep in mind. Yeah, and it moves around over time. Let's see here. I'm gonna share the screen. Where it's so annoying to get this stuff. Okay. Moodle. Scroll down. Resistor extra credit and resistor extra credit tips. So there's this one. Do you guys get the basic idea of this? It's not a flat circuit. It's a circuit with 12 legs to it. It's a cube. Every edge of the cube gets an identical resistor. So those are all resistance R, and on the back side, they're all resistance R in a different arrangement, kind of a flat arrangement. These are all R, and then the question is basically the second and third ones here. What is the equivalent resistance between AH, which you might call the cube diagonal, and then you're going to be asked to do AD across one face, opposite corners of one face, or maybe just across like one edge or one leg AB. Okay. Let me just briefly say how I would basically go about thinking about this. And there's more than one way to do this, but I say to do it this way. Okay, take the pair of leads they mention, take the pair of points they mention, and imagine a wire sticking into A and let's say out at H. And I would then say, let's have an arbitrary amount of current flow into A and out of H. we did something like this once. We put a battery across a complicated resistance setup, and we said, let's just have there be an arbitrary battery voltage. I'm going to do it slightly differently and say, let's say there's an arbitrary current I flowing in at one point and out at the other. And extra credit tips the cube. And this is giving it away. I was going to build up this. I mean, I said I would give the answer for AH. And then what you want to do is you want to try to imagine how will the current split and flow across these 12 wires as it works its way from input to output. And if you move the output, the way it splits becomes different. But if you do AH, there's overall 12 wires. And if all the resistances were different, you'd have to label every wire with a different current variable. There'd be I1 to I12. And then you'd have to write up 12 equations based on node rule and loop rule and solve like a linear set of 12 equations and 12 unknowns. And the result of that calculation would be to say, here's what fraction of I, here's the fraction of I that goes A to C. Here's the fraction of I that goes C to G, and you'd have all the fractions. And then you could use that to figure out the voltage drop from input node to output node. Now, if there's a lot of symmetry, there's way less than 12 different currents. Yeah. If there's, and the easiest situation is AH because AH has the most repetition, the most symmetry, I would say. And I would say basically you can get by with as few as how many resistances if you do AA. There's not resistances. How many currents do you actually need that are different than one another? All 3 wires spiking out of A will get the same current. All 3 wires coming together at H will get the same current as each other. It'll be the same as the current for the input wires. And overall, does this kind of seem about right? You could get by with 2 values. And now it's not 6 equations, sorry, it's not 12 equations and 12 unknowns. It's, I need 2 equations. And I get to go to nodes and loops to build my equations. Does anybody want to guess what fraction of the current equals I1? Well, right here, what does the node rule of that node say? Input I, output I1, I1, I1. So what's I1? It's a third of the total. And what's the green I2? You can look at any of these other nodes. It's half of I1. So it's a sixth of the total. And it won't go that quickly for AD because you're going to need more than 2 currents, but something kind of like that. So what's the answer for equivalent resistance A to H?